We're going to begin talking about graphing logarithmic functions. Logarithmic functions are the inverse to the exponential functions that we've talked about. So far, all the exponentials we've dealt with, we can either do via calculator, or we've known the basis and got the basis the same. But the logarithm functions are the functions that are the opposite or the inverse of those, and that's how we get rid of those. All right, we're going to take a look at graphing those today. We're going to start this by completing the table. Now, I've got a video. Hopefully you should be able to see this if I did this right, posted on the left, or on the right, excuse me, of your CAMI assignment. But I've got this table already pulled up, so I'm going to go ahead and put these answers in here. The base 2, first of all, and I'm not going to write this every time, but understand that base 2, that means 2 to the negative 2 power. What we need to remember, that is 1 over 2 squared. Remember, the negative exponents mean that they belong on the other side of the denominator numerator situation. So in this case, we move this and we learn that negative 2 is a 1/4. 2 to the negative 1 power is 1/2. Anything to the 0 power is 1. Anything to the 1 power is itself. And anything to the, not anything, 2 to the second power is 4. All right, what we're going to look at is the logarithm function, and we're actually going to pick inverses on this just to show you that this is what this looks like. If you went and looked through the table like this one, you'd learn, hey, that's undefined. That one is undefined. 0 is undefined. We'll talk about why that is later, but for now, that's what we're going to look at, is just what we can do. So we're going to look at some other points that actually have some values, first of which is going to be the x value of 1 is 0. And x value of 2 is 1, and that's actually a logarithmic property, which we will talk about later. We're going to skip 3. Well, we'll do 3. 3 is a decimal answer. It's an irrational answer, but it's 1.585. It's an approximation because it's not an exact. And then 4, 2. And let's see if there's another integer close. There is. Let's put 8, 3. So keep an eye on those two tables and see if you can recognize what these two look like. It says graph both of these on the same grid. Now, if you have your Desmos, you can take a look at these, but what we're going to look at is over here on the left side and graph the two on this little section we have over here. So I'm going to pull up and put a coordinate planes in my grid line here, and we will take a look at what these look like. Not the straightest lines, but see if we can fix that. And we're going to see if we can notice anything about these lines. So let's go ahead and plot the points to the exponential function, which we're familiar with. This, remember, is a growing function here, exponential growth, because the base is 2. But we have an ordered pair at negative 2, 1/4. We have an ordered pair at negative 1, 1/2. Ordered pair 0, 1. Ordered pair 1, 2. And then we ended with a 2, 4. So this is what this exponential function looks like. Not very pretty, but there it is. And our ordered pairs for our logarithms. Well, there's an ordered pair at 1, 0, 2, 1, 3, 1.5, 4, 2, and then off the graph is 8, 3. Now, if we had some negative numbers, this ends up getting undefined, but I'm going to go ahead and pick a number, put it in here for you, one that I know why it's important, because I'm a little familiar with these. And I'm going to look up the value 1/2. 1/2 is -1. And then we'll look up another value, which is 0.25, and it's -2. And then what we develop is this. Now, think about what I just got on those points, but let's visually take a look and see what we see. So we graph them both on the same grid. That's what we've got going there. This is B. What is the x-intercepts, y-intercepts? Well, for the f of x function, it does not have an x-intercept. It's asymptoting at the x, so f of x only has a y-intercept, and that y-intercept is at 0, 1. The x-intercept is not available. We don't have one. And then we would look at the log base 2. Well, the log base 2 has a x-intercept, and its x-intercept is at 1, 0, and its y-intercept, if we look at it, well, it asymptoted at the y value, so it has no y-intercept. That does not mean it cannot have one, but the parent function does not have one. We'll talk about transformations tomorrow, but as of now, this is all we're looking at. All right, it says, what is the line of symmetry between these two lines? Well, the line of symmetry, you can see that these have a reflection of one another. And our line of symmetry, if we did our y equals mx plus b, the equation of this line right here would be a y-intercept of 0 and a slope of 1, so that would be y equal to x. So our line of symmetry for this function is y equal to x. State the domain and the range of each of these. Let's slide this up a little bit here. Well, the domain, we'll start color coordinate these. For the f of x, the domain, remember the domain of all exponential functions is all real numbers. So it's from -infinity to +infinity. And its range, and this one was not manipulated. Remember, that's up or down. Let me change my colors. I just realized I graphed in red, so let's stick to red. The domain is all real numbers from -infinity to +infinity. And the range, we look at that graph, we can see, well, it's starting at 0 and moving up, so that would be from 0 to infinity. So we look at the g of x function, and we just try to take a look and see what this graph is doing. Well, we can see that its domain is not all real numbers because it is asymptoting at y equal to 0. So or x equal to 0, excuse me. So the domain of this is going to be from 0 up to infinity, because this graph continues to run right and it stops at the 0. And if we look at its range, again, range is up or down. Well, it's reaching to -infinity. So we got that going for us. And it's also reaching to +infinity, because the further and further we go right, it's going to continue to grow. All right. So hopefully you're noticing a pattern developing between these two inverse functions. We'll address these directly in just a moment, but let's get these answers real quick. What is the end behavior of f of x? Well, remember the end behaviors are described as x approaches. So that means as we move right, we'll stick to the color coordination. As the f of x function, that is the red, approaches positive infinity, we'll do it first. As it approaches positive infinity, y also approaches positive infinity. And then our second end behavior is as it goes to -infinity. as x approaches negative infinity, the y function is approaching 0. It's getting closer and closer to 0, but it's never going to touch it. And then our second function, as we go further and further to the right, that's positive infinity, this function is approaching positive infinity. And as x approaches negative infinity, this function does not approach negative x equal to negative infinity. It has an end behavior where x approaches 0. So as x approaches 0, y approaches negative infinity. Because the x doesn't go any further than 0, but the closer and closer it gets to 0, the closer and closer y gets to negative infinity, meaning it's dying down. It's getting smaller and smaller. Give you all a second. I'll leave that at the top there. Sorry. What is the equation for the asymptote of these functions? Well, we've already done the exponentials. Remember, the asymptote for these are y equal to 0. The asymptote of the logarithmic function, though, was a vertical asymptote, and it is an x equal to 0. And that's important to remember. We'll get into transformations tomorrow, but if there is no transformations, these are our asymptote equations for our asymptotes. So that is our log base 2. Now, what you need to understand about logs is just like with exponentials, we can change those bases. This one just happens to be a log base 2. And the log base 2, its whole purpose is to offset base 2. So if we wanted to offset base 3, we would have to use log base 3. So that's how these work. They're just inverse functions. There's an infinite number of log bases you can use. Now we're going to talk about the next log base, which is our natural log. We've already talked about the natural base. Now we're going to talk about the natural log. If we think back to our natural base, the e, remember e of 1 was that 2.71825 or whatever the number was, value. 2.389, excuse me. I got it here now. 7183, that's the number I'm looking for. So the natural log, since that's an irrational number, we can't just use the base 2.7183. The natural log, its purpose is to offset the natural base. So we're going to complete the table. I have these already posted here, so I'm going to go ahead and put these, and these are going to be decimal numbers. I'm going to write these in fraction form. I'd like for you to do the same. So on this one right here, my fraction form is actually e to the negative 2. I won't do this on all of them. That's equal to 1 over e squared. E to the negative 1 power is 1 over e. Now you can look up these numbers. These numbers are approximately 1.35 and 0.367. But we're going to leave it at that. Anything to the 0 power is 1. Anything to the 1 power is itself. Well, this would be e to the 1 power. That's that 2.7183 number. And then e squared is going to be 389. And I'm going to go ahead and write these decimal numbers to the other ones just so we can have an idea You can write them in the front too if you want. Just so we have an idea of where we're going. Now, these are the ones that are a little tougher because we're dealing with irrational numbers. We're dealing with irrational numbers here. So we're going to pick one for sure, and that is going to be the value 1, 0, excuse me. Yeah, 1, 0. Now, if I were to look up these values, what I would get is the inverse. Now, hopefully you noticed that on the last one, and we're going to do a little cheating here and actually put these in as the e's. That's what I was hoping for. If you go to Desmos or you go to your other calculator, you can actually put in 1 over e. If you put in 1 over e, you'll actually get -1. If you put in 1 over e squared, you're going to get -2. You can't really put in those decimal numbers because those are irrational numbers, and the irrational numbers are going to be not exact. So if you try to do that, it's just going to mess up a little bit. So if I were to look up e, I would get 1. If I were to look up e squared, I would get 2. Because what we've just learned is the inverse functions are always going to have inverse tables. Inverse functions are going to have inverse tables. Now we have the decimals over here, so we're going to do a little bit of cheating on this one. We know it's going to go through 0, 1, the exponential, and we know it's going to go through 2, 7 something. So it's basically 1 is about 3 and 2 is off the screen. And then we got a little bit of an asymptote going on here. So make this a little bigger. The e formula function looks like this. Now, everything about that will be the opposite on our logarithmic function. So I'm going to draw that symmetric line that we talked about last time. Not drawing it very straight, but there it goes. And the whole point of this is to show there's always going to be a reflection across this. There will be a teammate there. You see how far this one is from the line? There's going to be a point right there. This equidistance from the yellow line. We can also graph those ordered pairs. For instance, if we looked up 7.38 or 7.4 essentially, it's going to be at 2. That would be a point. And then we are asymptoting at the y-axis. And there you can see our symmetric point. So these graphs are symmetric because the functions are inverses. Anytime you have inverse functions, you have symmetrical functions. So f of x, let's talk about we'll write it in red. The x-intercept is not available because it's not crossing the x-intercept. And the y-intercept, surprise, surprise, we'll do the ordered pair, is 0, 1. And the g of x function is the complete inverse of that. I don't even look at the graph. If I know these two are inverse functions, whatever the other one had, this one is going to be inverted. So what I mean is this: the y-intercept was 0, 1, so the x-intercept is going to be 1, 0. The y-intercept was not available, undefined, whatever you want to call it. So this is going to be undefined. Our line of symmetry, already spoiled that one for you, is y equal to x. State the domain and the range of each of these intervals. So we'll do f of x, domain, range. Well, the domain of all exponential functions is all real numbers. The range is 0 to infinity if it's not transformed, which is what we will work on tomorrow. G of x, it's complete inverse. So since the range was 0 to infinity, the domain for the inverse of that is from 0 to infinity. And since the domain was all real numbers for the first, the inverse range will be the exact same thing. In behavior, our end behavior should be exactly the same. On the exponential function, as x goes to infinity, moving right forever, y is also going to infinity. And as x is going to negative infinity, and remember, that's just a fancy way of just saying moving left. As we move left, y approaches 0. On the logarithmic function, as we go infinitely to the right, this function is going to go infinitely up to positive infinity. And x doesn't go to negative infinity, it only approaches 0. But as it approaches 0, the function approaches negative infinity. And again, you can see this is the complete opposite inverse of the exponential function. All right, and then lastly, what is the domain of the asymptote? Well, the domain of the asymptote of e to the x power is x equal to 0. Y equal to 0, excuse me. And the asymptote for the logarithm is x equal to 0. I wrote it right, said it wrong. On the e, that is. All right, so this is actually where we're going to end today. Hopefully, if I did things right, you should have a little stop sign here. And this is where we will pick up tomorrow, is on the transformations.